Hello and welcome to some physics revision.
With me, Connor Durkin.
And me, Will Carne. Today we'll be going through everything you need to know for an A star in the A-level.
Focusing on the AQA course, but the topics may apply to other courses, so hello to you all,
Hello
lovely
to you.
people.
If you have any questions or comments, then you're very welcome to ask down there in the description.
Not the description.
The
it's
comments. You
Why
want to
would
go
ask
ask
me
in the description, you have fun with that. Right, let's begin, Connor,
with conservation of momentum.
Yes, and with linear momentum, or P, which is given by P equals M times V.
It does indeed, where m is the mass and v is the velocity, with the units of p being kilograms per metre per second. No, kilograms metre per second.
What are we doing with you, Connor? What am I going to do with you? Right. The principle of momentum states that, assuming no external forces act, the linear momentum is always conserved.
So the total momentum before collision equals the total momentum afterwards. So
P before equals P after. Really?
An elastic collision is one where momentum is conserved and kinetic energy is conserved. The equation for the kinetic energy is given by EK equals half mv squared.
Where EK is obviously kinetic energy. If kinetic energy is not conserved, then some of the EK is converted into other forms of energy during the collision. However,
please do remember that linear momentum is always conserved.
And total energy is always conserved as well.
Overall, it's just energy loss, maybe,
Yes.
Mucking up the numbers.
Right. Force, momentum, and impulse.
Don't be so impulsive.
Now, as you should know by now, Newton's second law for constant mass is
F equals ma.
So for a given force, the more mass you have, the less acceleration you will get.
The unit of force being newtons.
As acceleration is the rate of change of velocity, you can get a formula for F in terms of P.
F equals m times delta v over delta t.
Which is delta mv over delta t.
Which equals delta p over delta t.
Where P is the... So therefore, the resultant force is the rate of change of momentum.
Da, 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 da.
As delta mv is just mv minus mu, where v is your final velocity and u is your initial velocity, or just the change of momentum, then...
F equals mv minus mu over delta t.
Isn't that just lovely?
That's lovely.
Now Newton's second law can then be rearranged to give delta t multiplied by F equals mv minus mu.
Newton is a babe.
And impulse is defined as the product of the force and time, or Ft. Really? So that's what impulse is?
That pretty equation.
Yes,
Ooh.
that one there. So therefore, the impulse on an object is equal to the change of momentum of the object measured in Newton's seconds.
Da, 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 da. This is hence the area under a force-time graph. Look at that.
Isn't that lovely?
That's lovely. Mm-hmm. The force of an impact can be reduced by increasing t, as shown with this example of a chick and a duck.
You ready? There's a duck. Then
Oh.
the chicken comes in, but it barely does anything, right? Because he's
going
going slowly.
Yeah.
However, if he has more boom, then look at that.
The duck quivers.
Yeah, because the time's shorter. So
That's how airbags work as well, by the way.
Right.
I struggled understanding that at GCSE.
Circular motion now, so that we can study things moving in circles.
Spinning around. That's copyrighted. A quick maths lesson. The angle theta in radians is equal to the arc length divided by the radius of a circle, or as you should know it,
Theta in radians equals theta in degrees multiplied by 2 pi over 360.
the angular speed is the angle an object moves per second, given by, is that omega? I believe it's omega.
Yes.
Omega, the unit is rad per second, and it is given by...
the angular speed equals theta over t over time.
I think it's omega. The linear speed, v, and angular speed are then linked with...
v over r, where obviously v is linear speed, and r is the radius of the little circly thing.
Indeed. Circular motion has a frequency and a period, not to be confused with the frequency of its periods, which is roughly once a month. That's
the frequency f is a number
Wow.
of complete revolutions per second measured in hertz, and the period t is the time taken for one complete revolution in seconds, given by
F equals 1 over t.
and therefore t equals 1 over f.
For a complete circle, an object turns through 2 pi radians in time t. Therefore, you can get the equations.
The angular speed equals 2 pi over t, or 2 pi multiplied by f.
By the way, when you confused the omega thing, we were talking about the little squiggly W thing.
Yeah, they can see it on screen.
Ah.
Yeah, obviously.
Just checking. Yeah,
Right, centripetal force and acceleration. Go!
Objects
Quicker,
travelling in
let's
a
go.
circle have a constantly changing velocity due to their changing direction. This is acceleration, and in this case it is called the centripetal acceleration, and is always directed towards the centre of the circle.
Yes, that's why the direction changes, basically. The formula can be derived, but here it is for angular or linear speed, where AC is centripetal acceleration.
AC equals v squared over r, which equals omega squared times r. Note that they are speeds, so don't involve direction.
Now, Newton's first law states that an object's velocity will stay the same unless there is a force acting on it. Since object is accelerating, there must be a driving force, and in this case, it is the centripetal force, or centripetal force.
Centripetal.
Acting
towards the centre of the circle. Using F equals ma, you can deduce that Fc equals m times v squared over r, and that also equals m times omega squared times r.
If we've got omega wrong, then I do apologise, but you can see what it is.
We'll just overdub it with whenever we say omega, we'll just go W. And completely different. We'll get a woman to do it. There we go. No.
Remove this force, and the object would fly off at a tangent.
A complete tangent, straight line. That's how it works.
That's what a tangent is.
Yeah, but people don't know that because people might do physics and not maths. Moving onwards, simple harmonic motion. This is a lovely, disgusting unit.
Or SHM, not to be confused with SNM. Now, that is in Sci A5.
No, it's not.
Yes, it is.
Yes, it is. Well, I might have not gotten to it yet.
At least that's what our physics teacher told us.
No, we can't say that.
Yeah, we can.
It's nice.
An object moving with SHM oscillates back and forth about the equilibrium position, where the distance from the equilibrium is displacement x.
We can't call our teacher by his name. We have to call him Master now. Definition of SHM is an oscillation in which the direction of an acceleration of an object is directly proportional to its displacement from its equilibrium position, directed towards the equilibrium.
Drawing graphs of features. The displacement will be a cosine or a sine graph with a maximum value of a, which is the amplitude. It will be cosine if it begins displaced, and sine if it begins from the equilibrium.
The velocity will be the gradient of the displacement time graph with a maximum value of 2 pi fa.
It will.
It will be.
The acceleration will be the gradient of the velocity time graph with a maximum value of 2 pi f all squared a.
The phase difference is a measure of how one wave lags behind the other, measured in radians, degrees, or fractions of a cycle.
Two waves in phase have a phase difference of 0, or multiples of 2 pi radians.
Two waves anti-phase have a phase difference of pi radians.
So velocity is pi 2 radians out of phase with displacement, and acceleration is pi 2 radians ahead of velocity. So antiphase with displacement.
In SHM, F and T are independent of amplitude A, at least to an extent.
The kinetic energy varies according to the system. In a pendulum, by potential energy, EP, and in a mass spring system, by elastic potential energy, or EP.
That's really helpful.
As EP decreases, then EK increases to the equilibrium position where it swaps.
The sum of EP and EK is the mechanical energy, which is constant as long as the motion isn't dampened.
Yes.
Damped.
Dampened.
That's not the right word.
Dampened.
Now moving onwards. Calculations with SHM.
One way to think of SHM is viewing an orbiting object in the plane of the orbit. So using this, you can sort of see how speed, v, appears fastest when x is 0 and slowest when x is plus or minus a.
Using this model, you can gain the equation x equals a cos, and then in brackets 2 pi ft, which also equals a cos omega t.
Yes.
However, when the system is not displaced at all, i.e. begins from the equilibrium position, use the equation...
The same, but with sine.
So x equals a sine 2 pi ft.
But they know. It's just not been displaced.
It will be on the screen. It's fine.
Yeah, we know, but they know. It is on the screen. They can see it. Then using the equations for acceleration, you can deduce that a equals minus 2 pi f square, all squared, multiplied by x. There's a negative sign just because the acceleration is always towards the centre. Therefore, the opposite to the direction of motion. Apart from at the equilibrium where it's 0, and therefore the minus doesn't matter.
The maximum acceleration is when x is the amplitude a, so...
A max equals 2 pi f all squared a.
Yay!
See, we just swapped x
As this is the magnitude, it is always a positive value.
So that's why there's no minus.
Then, using the equations for velocity, you can deduce...
that v equals plus or minus 2 pi f multiplied by the square root of a squared minus x.
The plus or minus depends on the direction that the object is moving, and then you can get the maximum velocity as...
just 2 pi fa, really, because the x isn't there, so it's just square root of a squared, which is just a, mate. Isn't it?
Isn't it though?
This is in the middle, so where x is 0, as we saw by the EK-EP thing on the last slide.
Moving on. Simple harmonic oscillators.
Yay!
I like oscillates.
A mass on a spring is a simple harmonic oscillator. When the mass is pushed or pulled either side of the equilibrium position, there's a restoring force exerted on it.
The size and direction of the force is given by Hooke's law, F equals minus k to the x, where F is the restoring force, k is the spring constant, and x is the displacement from equilibrium.
Now, using F equals ma, you can rearrange this where the acceleration is minus 2 pi f all squared x to get F equals 1 over 2 pi multiplied by the square root of k over m, where k is a spring constant.
Or T equals 2 pi multiplied by the square root of m over k, where k is still the spring constant.
Yeah, as you can see, we've just done 1 over because it's T instead of F. And
Yes.
using the mass spring system and these equations, you can deduce that T is proportional to the root of m, and therefore T squared is proportional to m. Isn't that lovely,
That's
Connor?
lovely. I love squares.
And also you can deduce
That T is proportional to 1 over k, and also that T squared...
root 1 over k.
Oh, I'm so sorry.
It's alright, they can see.
T squared is proportional to 1 over k.
There we go. It is helpful to remember that in parallel, k total is just k1 plus k2, etc., etc. But in series, 1 over k total is the sum of 1 over k1 plus 1
It's
over.
like circuits and resistance, but different.
And finally, since t doesn't depend on a graph comparing the two will just be a horizontal line.
Similarly, using a simple pendulum, you can deduce that F equals 1 over 2 pi multiplied by G over L, or T equals 2 pi multiplied by the square root of 1 over G.
Yes, where
L over
G
L over
is
G.
L over G. Where G is the gravitational field strength and L is the length of the pendulum. To derive this, you approximate sine theta as 0, and therefore it only works with the small angles of around 10 degrees or less, which is
To an extent, little disclaimer.
kind of what we spoke about.
Yeah.
Now you can also see what T is proportional to using those formulae. Remembering just what we did earlier, really. Instead of wasting our time, we just swapped the letters over. So there we are.
Just
Have a
make
look
sure
at
you
that.
take the equations from the actual writing, not us, because I get it wrong a lot.
Free and forced vibrations.
I'm picking up forced vibrations. That's copyright, damn it. Free
What are you
vibrations
doing?
involve no transfer of energy to or from the surroundings. If struck, it will oscillate at its natural frequency, Fn, theoretically forever, minus dampening.
Force vibrations happen when there is an external driving force. The frequency of this force is called the driving frequency.
When the driving frequency approaches the natural frequency, the system gains more and more energy from the driving force, so it vibrates with rapidly increasing amplitude. When this happens, the system is resonating.
I'm doing an example.
This
graph shows how A changes with the driving frequency.
In practice, any oscillating system loses energy to its surroundings due to frictional forces like air resistance. These are called the damping forces.
Light damped systems take a long time to stop oscillating.
Whereas heavy damped systems take less time to stop oscillating. The time period T should remain constant, so when drawing a graph, keep that in mind.
Critically damped systems have reduced amplitude in the shortest possible time.
Systems are over-damped if they are critically damped, but take longer to rest. I like to think of it as a bit like roller coasters' brakes. You slow a lot suddenly, and then there's a gradual slow to complete stop, or rest. This analogy really isn't applicable to It's a Small World after all at Disneyland, but, that's a pretty wild ride if you think about it. It is a small world. It is a small world.
It's a small world.
I thought it was It's a Tiny World. That's the American one.
It's a tiny.
Oh, that's the Family Guy spoof of it. I remember now.
Plastic deformation of ductile materials reduces the amplitude as energy is absorbed, making smaller oscillations.
The effect of increasing levels of damping on oscillations near the natural frequency can be shown on a graph, as can pretty much everything.
Lightly damped systems have a very sharp peak. Their amplitude only increases dramatically when the driving frequency is close to the natural frequency, Fn.
As seen, for heavier damped systems, resonance occurs at a lower driving frequency than the natural frequency.
'Tis all true. Right, that's it. That's everything. Did you know
everything.
that? That's everything.
Everything.
Well, that's everything for part 1, which has been all about, can you remember? Further mechanics, because there's always more mechanics.
Everyone loves mechanics.
Next time we're doing a bit of gravity and electrics. We're loving that, so we'll see you for that. If you want help with the AS, then there's loads of AS videos. We've got maths videos, psychology videos, a few history videos.
Only the first year, though.
Some
we're
fun
we're so
videos.
sorry to those people doing A2, but we didn't do A2.
Yeah, okay.
Okay.
I love the advertising relentlessly at the end of the video. And you could always subscribe or comment or say something. If you've got any issues, then just ask Dan in the comments.
Yeah. The description will get you nowhere. I've been Connor Durkin.
And I've been Will Carne.
Have a very nice day.
Bye.
Bye-bye now. Bye-bye. Bye-bye. Send help.